And this is my final example of floating point conversion. So we take this fraction. So once again, the integral part is 0, so I write down as 0. Then we take the fraction, multiply by 2, I write down result, keep multiplying the fractional part by 2, keep multiplying, eventually get to 1.25, then taking this multiplied by 2, 1.5, and we get 1.0. So the rest of the precision points just going to be 0. Okay, so this is then I kind of project this 0.00000101 to our denormalized version. So this is a binary version of this decimal value. So of course it's denormalized, so we have to normalize it, and we're normalizing it by finding our first significant digit and moving the radix point 1, 2, 3, 4, 5 times to the right, which means that our exponent is going to be -5. So we multiply the normalized version by this exponent, and of course it means that we're taking this number and dividing it by 2 raised to the 5th power, right? So we're not really multiplying by dividing it by 2 raised to the 5th power. So this exponent -5 has to be stored as 127 minus 5, which is 122, which is this binary value. So we get our exponent, so the sign of course is positive, which is 0. We get our exponent, and this is our mantissa, the normalized version. So, right, so we can just copy it over here, and the rest we can fill with zeros. Okay, correct number of zeros. Quick observation that it is actually stored very precisely, since it is fully assembled from base to fractions. So this is a dyadic fraction. So let's quickly verify the result in our converter. And so we get our result, which is stored very precisely.